Hi, Year 12, here we are again, and this is Nuclear Reactions Part 2, and this is to do with half-life. Okay, there's three different ways of defining half-life. So one is it's the time it takes for the parent nuclei to decay by half. So if you've got 100 kilograms of your parent nuclei, and it's half of it falls apart, the time it took to do that is the half-life. So if you've got uranium-238, 100 kilograms of it, and you left it for a few thousand years, then you would come back and you'd find you've only got 50 kilograms of it because the rest of it is decayed into something else. Okay. It's also defined as the time it takes for the daughter nuclei to double. So if your uranium-238 was falling apart into thorium, then the time it takes for the amount of thorium to double is the same amount of time. It's the half-life. And it's also the time it takes for the amount of ionizing radiation from that reaction to half. So if there was 10,000 counts per second coming from your uranium-238 at the start, and there was 5,000 counts per second after one half-life, then there's your definition. Alright, there's an equation, this one here. By the way, you need to look at the photograph which has gone with this video to get a better picture of the board which I'm stood in front of. So, if you look in the book on page 158, it's got a slightly different version of this equation, and I've done it as a different version here to show you that you can do it different ways. This way is slightly easier to understand. So what? Your mass of the remaining nuclei equals the mass of the parent nuclei divided by 2 to the power of n. And here is an example of how that would work. So, n's the number of half-lives, by the way. If you had carbon-14 and it's got a half-life of 5,700 years, and you had 50 kilograms of it, and after 5,700 years you would have 25 kilograms. The way the equation works would be 25, that's the stuff at the end, 25 kilograms at the end, 50 kilograms at the start, and divide it by 2 to the power of 1. 2 to the power of 1 is 2, so it's 50 divided by 2 equals 25. Amazingly simple. The next half-life would look like this, so you would have 12 and a half, because that's half of 25, equals 50. That's your original amount, divided by 2 to the power of 2. The reason it is to the power of 2 because it's had 2 half-lives since the start, and n is the number of half-lives. It says so here. Alright, for those that can't cope with the algebra, which actually isn't that bad, you can graph it like this. This is exactly the same. Look, 50 kilograms at the start, at time 0. And after 5,700 years you would have 25 kilograms. Next you would have 12.5 kilograms, and that would be at 11,400 years. I'll put it all up here for you on this little table. So each time the 50 halves to 25, to 12.5, to 6.25, and then to 3 point not very much. And each time we add 5,700 years onto the time. Why is carbon-14? Well, because it's important for doing carbon dating. Alright, so there's how half-lives work. You can expect a question on half-lives in the test. I'll put the page numbers of the questions that you need to do on the board, on Classroom, and this should sort us out for the double period on Monday morning. Thanks!